After 1 day, the schematic diagram is complete at 95% approximately. You can see this part here, the VG1000J. I didn't find anything on internet with this reference, but with the reverse engineering we can guess what is this part. This board is a logic board which permits to drive the solenoids, the relays, the lamps and so on. So we can see, for example, this part we have actually 3 outputs here, pin 14, pin 8, pin 7. You can see that the adjacent pin is connected to ground here, pin 9, pin 13, pin 7. Actually this circuit here, pin 1, 2, 3, permits to drive the crowbar which is on the power supply board. Actually this part is a quad MOSFET. The drain is here, pin 14, pin 8, pin 7 and pin 1. The source corresponds to pins 13, 9, 6 and 2 here, and the grids of the MOSFETs are here 12, 10, 6 and 3. The schematics, like it is very complicated, it is difficult to understand, so therefore I will replace this part by 4 MOSFETs and the schematic diagram will be much more readable. I did the complete reverse engineering of this coffee machine. It was not so easy, but you can see on the screen the complete schematic diagram of this machine. It's correct, I think, at 99%. As you can see, there are 4 blocks. On the bottom left here there is a power supply. On the top here there is a temperature controller. On the right there is a logic circuit which permits to drive the 2 solenoids here for the coffee and the tea. And here there is a front end for 2 capacitive sensors, the server probe here and the water level on the tank, which is this sensor here. Okay, so let's see the power supply first. Now this is the power supply of this coffee machine. The circular connector is here. There are 3 phases here, phase A, B and C, and 1 neutral line connected to terminal E of the connector. The central pin here is connected to the mechanical ground. This is the protective earth. The heaters are here. They are connected to the connector through a power relay here. 3 thermal breakers. Phase A is also connected to the low power circuit, okay, which is actually the rest of the circuit. There is a fuse here and the on-off switch. The voltage of 115 volts is fed to this transformer. The secondary is approximately 20 volts. You can see the hot plate also, which is connected to phase A, okay, through this switch here. So there is also a lamp connected to 24 volts, which is activated at the same time than the heaters of the hot plate here. I have measured the resistance of 390 ohms. So therefore the power is approximately 33-34 watts. We have on the secondary a fuse here and 4 diodes for full wave rectifying. And we can see 2 regulators LM117. One permits the generation of a voltage of 24 volts and there is another voltage here of 13.8 volts after calculation here. We will see later the circuit here on the bottom. See the modifications are required for a connection to mains 50 or 60 Hz. For 115 volts it is straightforward. We need to connect 115 volts between the neutral here and the phase A, which is terminal B of the circular connector. Okay, the power will be 900 watts. If you want 1800 watts, you can connect together terminals B and C. For this voltage, 115 volts, the only thing to change is the transformer. So it It is possible to replace the transformer by an AC to DC converter. I have estimated the power to 20 watts approximately. For 230 volts, it is more complicated. The idea is to use the two heaters in series, so therefore the neutral will not be used. Okay, and 230 volts will be applied between terminals B here and C, for example. The power will be 1800 watts. Okay, so the transformer will be replaced by the same AC to DC converter. The problem concerns the hot plate here, which requires a voltage of 115 volts here. Therefore, it is possible to cut this connection here on the PCB and to place a dimmer circuit like this. I have designed a small PCB which actually replaces the transformer. The pinout of the PCB is compatible with the transformer. For the AC to DC converter, I have chosen this model. The total power is 30 watts plus and minus 15 volts. This model is quite small. It fits under the coffee machine. It is not very cheap, approximately 50 euros. Okay, so this is this model, plus and minus 15 volts amp. Okay, we can see the length is approximately 88 millimeters and the width approximately 35 millimeters. We can see here the bottom side of this coffee machine. We can see here on the left the heater for the hot plate. We can see also here the three heaters for the water tank, which is here. And we can see the AC to DC converter. I have added 6 spacers on this metallic stuff here. The length of the spacers is 12 millimeters. Okay, I have added also an insulation plate here between the power supply and this metallic stuff here. We can see on the screen the temperature controller circuit. The temperature sensor is here. It is the NTC thermistor 100K. The thermistor is connected between the power supply VCC here with a voltage of 13.8 volts and a pull-down resistor of 21 kilo ohms. So therefore the voltage across this resistor increases when the temperature increases. This voltage is fed to two comparators, this one and this one. So let's see the first comparator. We can see that we have the same resistor here, 21 kilo ohm. When the temperature is above a given value, the output of this comparator is at high level. The threshold is given by this resistor. It gives a temperature of 0 degree Celsius here. Therefore, the output is at high level for temperature above 0 degree. The second comparator has an adjustable threshold, which is given by this trimmer. I have calculated the minimum temperature of 84 degrees and the maximum temperature of 108 degrees. And this temperature permits regulation of the temperature of the tank. So we can see several outputs here. So let's see this one, for example. This MOSFET permits to activate the on-off lamp. So we can see that the on-off lamp is activated when the temperature is above 0 degree and also when the water tank is not empty. So there is a second lamp here, which is a no water lamp. The no water lamp is activated when the signal is at low level. In that case, this MOSFET is off and this one is on, thanks to the pull-up here. The third output is the heater relay. The heater relay is activated when the temperature here is below the temperature which is set by this trimmer. Okay, the relay is off also when the temperature is below 0 degree. The heater relay is also deactivated when the water in the tank is not high enough. The temperature voltage here, VTH, is also fed to the crowbar circuit we are going to see now. The sensor voltage is also fed to a third comparator, which is this one. Okay, so we can see the same resistor, 21 kilo ohms. Therefore, the temperature threshold is achieved when the value of the thermistor is exactly this value here, 4K22, and this temperature is approximately 119 degrees. Okay, so this is actually a protection. This circuit is called a crowbar. When the temperature is above 119 degrees, there is a high level at the output of this comparator. This is an op-amp actually. This N-channel MOSFET turns on, so therefore there is a current flowing through this resistor, this diode, the MOSFET. Okay, and this current permits to activate this SCR. Okay, so this SCR provides more or less a short circuit between this point and the ground. So therefore there is a high current flowing through the SCR, through the ground, and the current returns to this diode here, to the fuse, okay, like that. Okay, so the goal is to blow the fuse. This circuit permits to avoid a high temperature, okay, on the tank. This is the logic circuit for the activation of the solenoid. There are two solenoids. The solenoid permits to activate the valve, okay, for the coffee or the tea here. At a given time, only one is activated thanks to this relay here. Okay, and we need also that this transistor is on. Actually, there are two transistors in parallel. Okay, so let's see this circuit, which is actually the main circuit for the activation of the solenoid. We can see on the left here the two push buttons for the coffee brew and tea. We can see that there are two flip-flops, one here and the second one here. So when one of these buttons is pressed, in that case there will be a high level at the output here. A high level here permits to activate the MOSFETs here if the two diodes here are off. One diode is connected here to the low water signal, which is at high level in normal mode. If the volume of water is not enough, there will be a low level here and the solenoid is not activated. The second diode is connected to the second flip-flop here. Okay, so let's see this second flip-flop. So you can see that one input here is connected to the reset line. The reset line is also connected to the first flip-flop. The second input of the flip-flop is connected to this OR gate here. One input of the OR gate is connected here, okay, to the comparator, which is at high level here when the temperature is below the normal temperature. So the first flip-flop permits to memorize action on the push button coffee or tea. So if the temperature is below the normal temperature, therefore there will be a low level on the diode and the solenoid is not activated. In that case, the temperature will increase until the temperature reaches the normal temperature. In that case, the signal will be at low level, and this permits to have a high level at this output here, and this permits to activate the solenoid. So therefore, this circuit permits to optimize the time. Even if the temperature of the water is not warm enough, you can press the coffee or the tea push button here, and when the temperature will be fine, the solenoid will be activated automatically. The last circuit is the front end for the server probe and the low water probe. Actually, there are two identical circuits. So let's see the circuit for the server probe, for example. The server probe is here. The probe is in the water. There will be a capacitance between these two terminals here. So one is connected to ground. It is the same for the low water probe. This is equivalent to a variable capacitance. There is a square wave generator. The frequency is approximately 600 Hz. Okay, so the signal is fed to the probe using this coupling capacitor this resistor here, another coupling capacitor, okay, and to the capacitance of the probe here. So therefore on that line there is a triangle signal. So this signal is fed to this comparator. The second input of this comparator is actually a square wave. Okay, the square wave is biased to the mid power supply using these two 10K resistors, and this resistor is connected also to the square wave. So on that line there is a square wave. So therefore on the output here there is rectangular signal. There is a phase detection using this diode here connected to the square wave. Okay, so the output here is rectified using this diode, this capacitor, and this leakage resistance. So therefore on that line there is a DC signal which depends actually on the capacitance of the server probe. Okay, so this voltage is fed to this comparator. Okay, the second input of the comparator is a constant voltage. Therefore, at the output of this comparator, there is a low level. Okay, when the capacitance here is present, the signal is fed to the reset line. So this permits actually to reset the cycle when the server is full. Okay, the second part of the circuit is identical. At the output of this comparator, there is a low level. Okay, when the volume of water is not enough inside the tank.